Welcome to the Nexenta product training series. This episode is all about Vdev layout and L2ARC sizing. The Vdevs, we're going to look at what a Vout is, how it matters, what the options are. From there, we'll go to L2ARC basics and the sizing of how it impacts your ZFS environment. First off, a Vdev is one or more disks that are combined together and work to store data all in one group. Normally, these are referred to as RAID sets. You have the option with ZFS to look at both mirrored and striped. Mirrored could have 2 or 3 drives, and then you can also look at different RAID Z options with both 1, 2, and 3 parity drives. A little bit of thing to make you think about how that impacts what you're going to do for a Vdev. You can look at a lot of different drives. In this example, there are 24 drives total. If you're looking for more capacity, you could look at just 2 Vdevs with 12 drives per. With that though, if you're looking at a 7200 RPM drive, you'll notice that you're only getting about 160 IOPS out of that configuration. Assuming that those are 1 terabyte drives, you're going to actually only get about 20 terabytes worth of capacity. The reason you only get 160 IOPS is because you actually only get the IOPS of 1 disk per Vdev. So when you're looking at a more balanced configuration, you could look at 3 Vdevs that have 8 drives per. This scenario, you could be looking at upwards of 240 IOPS, again, the 80 times 3. Now you're looking at only about 18 terabytes, so you're not dropping dramatically in capacity. This does change over scale though. This is all designed with 1 terabyte drives, however. Then you can go into like a performance optimized environment. I'm going to look at all mirrors, 24 drives, 2 mirrored sets, 12 Vdevs. With this, you're probably looking at about 960 IOPS, so a significant increase without dramatically dropping the capacity needs. When you're looking at how to design your Vdev, this is the way you should really consider how you're going to look at things. Whether you need a lot of performance, whether you need a lot of capacity, sometimes a balance is in between. The next thing to look at when you're looking at Vdevs is what's a Zpool. The Zpool is really an aggregate of Vdevs that are put together. You can have 1 or more Vdevs into a Zpool, and normally they are referred to as the volumes when you're looking at a configuration. It's actually really simple to think about. Hard drives go into a Vdev in the matter of a RAID set, then those Vdevs go into a Zpool. Zpool is what you're actually going to store your data on. So when you're creating shares and folders, they're actually coming off of your volumes, off of your Zpools. Now we're going to move into the L2ARC basics and some sizing. Traditionally, you had disk and RAM. That's all that your options were in a traditional server. Shortly, we started to see SSDs, and this is a more recent move. Those SSDs allowed us to have a lot better performance than the traditional disk. Think about where you could get 10,000, 15,000 IOPS out of a single disk, a single solid state. However, you were only getting 80, 120, 180 IOPS on average out of a 15K drive. You were looking at 10,000 IOPS or more out of a solid state drive. The way that ZFS looks at it is we actually take that memory and it becomes the ARC. We're going to dig into that in a moment. From the ARC, we also have a layer 2 of that ARC and the ZIL, the zero intent log. We'll also look at that in a moment. I know that we did some sessions on that earlier, so make sure you look at some of the other sessions and really learn a little more about the ZIL. Then we take that capacity drive and it becomes a disk storage pool. As we look at the ARC, the L2ARC, the ZIL, and the disk storage pool, one of the things that's key is to look at is that L2ARC. It's that level 2 adaptive replacement cache. Remember, the memory is your initial layer of adaptive replacement cache. When you have memory in a system, whatever you have outside of the storage for the OS, and then outside of things that are needed for metadata, become that initial cache. Anything outside of that, when you expand past the needs, and you can surpass what you need in the ARC, the L2ARC comes into play. It stores your frequently read data that exceeds that. You can use the L2ARC. We'll actually use RAM from the ARC as well. It does need to have the metadata. So bear in mind when you're looking at your configurations, when you have ARC and you have L2ARC, there needs to be a proportion. The L2ARC needs some ARC, some of the space from the ARC, some of the memory for the metadata to know how the L2ARC is managed. One of the also key notes about looking at ZFS and looking at the L2ARC is a failure of your L2ARC is not going to result in a loss of data. But the performance of the Zpool could be degraded because you don't have that extra cache. You can still get all the IOP off of your disk storage pool, and you'll still get some improvement from your ARC, and then you can simply just replace your L2ARC drives. When you're looking at cache, the key is to look at the ZFS structure. How does ZFS cache data? You look from all the way to the left, that's your reads and writes coming from your host system. So if you're looking at a SQL box, a database box, email, VMware, whatever it is, they're sending reads and writes in. The first place it hits is the ARC. One of the things you'll notice is that the L2ARC and the actual capacity drives, the HDDs, are not actually connected. The data is copied from one point to the other, but there is no direct interaction between them. So the first thing that data will do is look on the ARC if it wants to do a read. If it's not there, it'll look at the L2ARC. If it's not there, then it looks at the HDDs. If it's something that is either most recently used or most frequently used, using the algorithm that's built into ZFS, that data may be copied into the L2ARC. Bear in mind it will be copied and not moved to keep that data integrity that is key to ZFS. So how do blocks get to the L2ARC? The things to look at is it's not just the least recently used, the most recently used, or the most frequently used. There's actually an algorithm built into it, and the data moves from both the ARC to the L2ARC, and then actually just gets evicted out. We don't copy the data from the L2ARC onto the spinning disk. That data is already there. So if it's going to be evicted, it's officially looked at as in the scan range you'll see in the picture. That's the data that's eligible to be moved down into the L2ARC. You'll notice the red gets moved down, while it can, and other blocks are moved off. Maybe the most recently stuff needs to still sit in ARC because it's actively being used. So how are you going to size for L2ARC? The first thing to look at is determine the working set size. The working set size is really what part of your data is hot at any given time. Determining this can be quite difficult at times depending on how you're looking at it. If you have VMware machines, maybe that working set size is a component of your base image. If you're looking at a database, maybe it's the large database that you're accessing all the time. However, it might not be all the blocks of that. So you really have to consider what your working set size is. This is something that can change over time, and it may also mean that it'll impact how much L2ARC you want in your environment. That's how you're going to look at Vdev layout and L2ARC sizing. Thanks for joining us.